Welcome to the Deep Dive, where we extract the most powerful knowledge and the most surprising insights from dense technical sources, giving you the shortcut to being truly well-informed.
Today, we are taking a deep breath and plunging into the fundamental laws of physics. Not just the theory, but how they actually show up in high-resolution digital data.
Yeah, and our source material is, well, it's pretty intense. It's the second edition of Experiments and Demonstrations in Physics Bar Ilan Physics Laboratory.
It sounds incredibly specific, and it really is.
It's basically a guidebook for advanced physics teaching, right? It's
Yeah.
got 144 experiments, mechanics, optics, E&M, applied physics, the works.
And the key thing, the thing that runs through it all, is the use of modern computer-assisted setups. We're talking Pasco Systems, Science Workshop, Data Studio, Capstone software.
Okay.
So our mission today is really to get past the textbook equations and show you how these digital tools fundamentally change how we see the physical world.
Right. It's about that shift, isn't it? From, slowly taking readings and averaging them to getting instant, high precision, dynamic data.
Exactly. The precision of modern sensors just reveals things that used to be subtle or really complex to measure, transforms them into immediate visual proof.
Okay, let's unpack this. We're starting with something pretty foundational, something almost everyone bumps into. Elasticity. Hooke's law, $5 a Caxilloc.
Yeah, this is a perfect example of that digital leap we were talking about. Think back to the classic way you do this in school.
Oh, yeah. Hanging little weights on a spring, waiting for it to stop bouncing.
Right, measuring the stretch with a ruler, maybe plotting, half a dozen points if you're like, it's all very static.
And slow. And your points probably weren't perfectly lined up because, well, rulers and eyeballs aren't perfect. Took ages to draw the graph.
Exactly. Now, contrast that with the modern setup described in the source. You hook the spring up to a force sensor.
Okay.
And at the same time, a motion sensor is tracking the spring's extension,
Yeah.
usually bouncing a signal off a little reflector.
So you just gently pull the spring or maybe start it oscillating.
Yep. And here's the kicker. The software plots the force versus the extension in real time as it's happening.
Wow. So you see the straight line forming right there on the screen.
Instantly.
Yeah.
It's immediate, undeniable proof of that linear relationship.
Yeah.
You don't wait. You don't calculate later. The slope of that line, which gives you the spring constant, 20 KLA, they got like $14.05 texty arrow, and one example, it just appears.
That must really shift the focus in the lab, right? Less about the drudgery of measurement, more about seeing the physics instantly.
Absolutely. It frees you up. You can immediately move on to analyzing more complex things that are way harder to track manually, like, say, the oscillations of that same mass on the spring.
Okay, so sticking with the spring, but now letting it bounce freely.
Right. And we all know it doesn't bounce forever. The amplitude decays. It gets smaller over time.
Exponentially, right.
Exactly. It follows Manus-Delotio. That delta is the decay constant linked to things like air resistance, friction, and the mass itself. Delta lambda.
And measuring that decay accurately by hand would be tricky.
Very tricky. But the computer interface, it's logging maybe hundreds, even thousands of precise position readings every second.
So it can just map out that decaying curve perfectly.
Perfectly. And it can fit the data to that exponential equation and calculate the exact decay constant at the right there.
And they use this to check the theory, like seeing how the oscillation frequency changes if you double the mass.
Precisely. You're not just watching it slow down. You're quantifying exactly how quickly the energy is being lost.
It really highlights how these systems turn classic, maybe slightly messy experiments into super quick, high-precision measurements.
That's the core idea. And this rapid digital capture becomes even more crucial when you move from, say, a bouncing spring to looking at really fast, complex electrical signals.
Which naturally brings us to the workhorse of the modern electronics lab, the digital storage oscilloscope, the DSO.
Ah, yes, the DSO. The source calls it a blend of an analog scope speed and the computer's data crunching power. It's essential.
And the key specs are just mind-boggling, aren't they? The sample rates mentioned.
Yeah, they talk about models hitting 1.25 gigahertz. That's 1.25 billion measurements every second.
Billion, okay.
That kind of speed lets you capture incredibly fast, fleeting electrical events, things that would just be a blur or totally missed on older scopes.
And there's that feature you mentioned earlier, the infinite persistence. That sounds really useful for teaching or just for observing tricky signal.
Oh, it's revolutionary if you've ever used an old analog scope. On those, a quick pulse, or like the dying oscillation in an LCR circuit.
An LCR circuit being one with an inductor, capacitor, and resistor.
Correct. That decaying voltage signal would just flash on the screen once and poof, gone.
But with infinite persistence on a DSO.
It just stays there. The whole decaying pattern remains frozen on the screen until you choose to clear it. You can actually study those transient effects, those quick changes, without losing the picture milliseconds after it happens.
That's a huge advantage for understanding what's actually going on.
Definitely a game changer for observation. Now, moving from looking at signals to actually measuring fundamental forces, the manual covers some key electricity and magnetism demos.
Okay.
One is basically redoing Ørsted's classic discovery, showing an electric current makes a magnetic field. Simple but foundational.
Right, the compass needle moving near a wire.
Exactly. But the second one is, I think, brilliantly clever in how it uses modern sensors to measure the magnetic force. The Lorentz force, 1 equals QE, plus QV times BAO. How do you measure an invisible force precisely?
Good question. How do you?
You weigh it, sort of. The setup involves hanging a straight wire, carrying a current within a uniform magnetic field, maybe from a strong permanent magnet.
Okay.
Now, the magnetic force acts perpendicular to both the current and the field, so it pushes the wire either up or down.
Ah, so you connect the wire setup to a force sensor, like the one used for the spring.
Precisely. The force sensor, which is basically a very sensitive digital scale, measures this tiny change in the effective weight of the wire setup.
That's smart. So the data system plots the measured force versus the current you put through the wire.
And you get that expected straight-line relationship, confirming the theory.
Mm-hmm.
But the really neat part, the real aha moment, is when they flip the magnet over.
Reversing the magnetic field direction, which should reverse the force direction.
Yes. So depending on which way the magnet is oriented, the force sensor shows either a tiny increase in the measured weight or a tiny decrease.
Wow. You're literally seeing the magnetic force show up as a change on a scale. That's about as direct an observation as you can get.
It really is. Taking something invisible and making it directly quantitatively measurable like that.
Okay, this is fascinating. How does this level of digital precision help when we're looking at waves? Things like sound or light. Let's jump into optics. Maybe Malice's law. Polarization.
Good one. Malice's law describes how the intensity of polarized light changes when it passes through a second polarizer, called an analyzer. The law says the intensity, $1, is proportional to the cosine squared of the angle, theta, between the two polarizers. $1, IR to wata.
Right, so you need to measure both light intensity and the angle very accurately.
Exactly. Getting that precise angle measurement is the tricky part traditionally. You need really good angular resolution as you rotate that second polarizer.
And the digital fix is?
A rotary motion sensor. It hooks up to the analyzer and gives you a continuous high-resolution reading of the angle to theta rho.
Ah, okay. So that sensor tracks the angle, a light sensor measures the intensity.
And the software plots intensity versus angle in real time. You see that cost-to curve emerge beautifully. Trying to do that accurately with just protractor marks on the polarizers. Forget it. You just don't get the resolution.
And there's a detail in the book about the light source itself, isn't there? They insist on using a laser diode.
Yeah, they specifically say not to use a regular incandescent bulb.
Why is that?
It comes down to the polarizers they use. Apparently, they don't work well in the infrared part of the spectrum.
And incandescent bulbs put out a lot of heat, meaning lots of infrared light.
Exactly. That infrared would just go straight through unpolarized, messing up the intensity measurement. A laser diode gives you nice, clean, visible light that the polarizers can handle effectively. It's a neat reminder that the specific tools really matter in getting clean data.
Good point. Okay, let's switch from light waves to sound waves. The source has this fun name for a technique to measure the speed of sound. The BAT technique.
Yeah. They playfully mention it's like what bats have been doing for ages. It's a pulse echo method, and it's very accurate.
So how does it work with the sensors?
It relies on that synergy of sensors again. You use a motion sensor, the same kind used for the spring experiment, often. It sends out short pulses of ultrasound.
Okay, like a bat's chirp.
Kind of, yeah.
Yeah.
And it listens for the echo bouncing back off a reflector. Crucially, it measures the precise time interval, delta t, for that round trip.
Got it. But speed is distance over time. You need the distance, too.
And that's where the second sensor comes in. You mount the reflector in a way that its position, $6, can be precisely measured, often using a rotary motion sensor linked to its movement mechanism.
Ah, so one sensor gets the time of flight, the other gets the distance traveled.
Simultaneously, the system calculates the speed as ZOZ equals 2x delta TTE, the 2x because it's a round trip. It's elegant because you get high-res distance and time data together, canceling out a lot of potential errors.
Very clever. Now, somewhere in this section on waves and signals, there's a really important point about dealing with noise and measurements, right? The averaging technique.
Oh yeah, that's fundamental. Anyone dealing with real-world sensor data needs to understand this. It's about pulling a weak, often periodic signal from under a lot of background noise.
Especially that annoying hum from AC power lines, the 50 or 60 hertz noise that gets into everything.
That's the classic example. And the key insight, the really practical takeaway, is how long you should average for.
It needs to be specific, doesn't it?
It's extremely specific. The noise reduction works best, mathematically cancels out perfectly, if you average the incoming signal over exactly an integer number of periods of that unwanted noise frequency.
Okay, walk me through why that works.
Well, think about that 60 hertz hum. It's basically a sine wave. If you take any sine wave and average its value over one complete cycle,
The positive half cancels out the negative half.
perfectly, the average is 0. Same if you average over 2 cycles, or 3, or any whole number.
Ah, so by setting your digital averaging window to be precisely, say, 160th of a second or 260ths or 360ths,
You guarantee that the contribution from that 60 hertz noise averages out to 0, no matter where in its cycle it was when you started measuring. It just vanishes from the result, letting the real signal underneath shine through.
that's a brilliant piece of applied wave physics, using precise digital timing to effectively erase interference.
It really is. It shows how software control gives you power over signals that was just impossible with old analog filters. Okay, let's look at a couple of final examples from the more applied physics end of the spectrum in the source: superconductivity and fiber optics.
Right, superconductivity. That state where materials suddenly have zero electrical resistance below some critical temperature, 2 SOls.
That's the defining feature. But interestingly, the experiment described focuses on a magnetic property to detect the transition, not resistance itself.
How does that work? How do you use magnetism to see when something becomes superconducting?
They use something called a magnetic bridge. You can think of it like a sensitive balancing circuit, but for magnetic fields instead of voltages. It's designed to detect very small differences in magnetic flux between two paths.
Okay. And how does the superconductor affect the magnetic flux?
Ah, that's the Meissner effect. It's the other hallmark of superconductivity. Below 2s cells, the material abruptly kicks out any external magnetic field. It becomes perfectly diamagnetic.
Like a perfect magnetic shield.
Exactly. So as the sample cools through the terecitalis inside the magnetic bridge, there's this sudden dramatic change in the magnetic flux lines because the sample starts expelling them. The bridge detects this sharp change.
So spotting that sudden change in magnetic properties is actually an easier or cleaner way to pinpoint Tiriyata than trying to measure absolutely zero resistance, which can be tricky with noise.
That seems to be the implication, yes. It uses this distinct magnetic behavior as the indicator for the phase transition.
Clever. Okay, lastly, fiber optics. We know the big advantage is huge bandwidth because light frequency is so high, and it's immune to electrical noise, EMI.
Right. But the source points out a fundamental physical limit in basic optical fibers, the ones called step index fibers.
Step index means the core has one refractive index, and the cladding around it has a slightly lower one, causing light to bounce along inside.
Correct. But light rays can take different paths. Some go pretty much straight down the middle. Others bounce off the core walls at steeper angles, taking a longer zigzag path.
And if they're carrying bits of the same signal pulse, but travel different distances, they arrive at slightly different times.
Exactly. This is called modal dispersion. It causes the light pulses to spread out, to broaden as they travel down the fiber. This pulse broadening fundamentally limits how fast you can send data before the pulses overlap and become indistinguishable. Limits the bandwidth.
So what's the physics-based solution?
It's really ingenious. The graded index fiber. Instead of the sharp step in refractive index between core and cladding, the index of the core itself varies.
How does it vary?
It's highest right in the center of the core and gradually decreases towards the edge.
Okay. How does that help?
Remember that refractive index controls the speed of light in the material. Higher index means slower speed.
Ah. So the light rays taking the shortest path straight down the middle travel the slowest.
And the rays taking the longer zigzag paths near the edges are in a lower index material, so they travel faster.
Wow. The different speeds compensate for the different path lengths.
Precisely. The graded index cleverly equalizes the total travel time for all the different light modes. Pulses stay sharp, allowing for much higher data rates over long distances. It's a beautiful piece of physics engineering.
So bringing this all together, what's the big picture for you, the listener? This manual really drives home that modern physics, especially in education and research, is all about translating these complex dynamic events, bouncing springs, decaying signals, magnetic forces, light waves, into high-resolution digital data we can see and analyze instantly.
Yeah, the ability of these modern tools to capture things happening in real time with high precision, it just provides immediate confirmation for physical laws, stuff that honestly just decades ago required incredibly painstaking, error-prone measurements or was purely theoretical.
Mm.
It makes the physical world more quantifiable, more immediately accessible than ever.
It really feels like these experiments show that the most exciting physics isn't just chalk on a blackboard. It's about making these incredibly precise, fast measurements, things happening in milliseconds or microseconds, enabled by these powerful digital instruments.
Absolutely. And the tools themselves, like that DSO sampling at over 1 billion times a second, they force us to constantly push the boundaries of what we even can observe and verify experimentally.
Okay, let's leave you with a final thought to chew on, sparked by another experiment in the source. They measured the speed of electromagnetic waves in a standard coaxial cable, like your old TV cable.
And the speed wasn't the speed of light in vacuum. It was significantly slower, about $1.99 times 108 day and 8.
Right, roughly two-thirds the speed of light. And this slowdown meant a measurable delay. For just 100 meters of cable, the delay was 355 nanoseconds. That's 355 billionths of a second.
Seems tiny, but measurable with modern tools.
So here's the question. If even light slows down noticeably and creates measurable delays in just a simple 100-meter cable, what kind of fundamental speed limits and, maybe more importantly, processing bottlenecks are we really up against when we're trying to shunt massive amounts of data, financial trades, scientific results, streaming video across continents and around the entire planet? Where are the real delays in our interconnected world?